All right, here's a couple more problems involving rates of change. And so we have the radius r of a circle is increasing at a rate of 3 centimeters per minute. Find the rates of change of the area when r is equal to 6 and r is equal to 24. So now I'm using the problem here, and I say find the rates of change of the area. That means that I need an area equation. And so the area of a circle is equal to, there's a little dot in there. The area of a circle is equal to pi r squared. And so what I need to do is I need to find the rate the area is increasing and the rate of change of area. That means the rate of change is the derivative. So I'm going to take the time derivative of both sides. So the derivative of a with respect to t is equal to, now pi is a constant, so that just kind of comes out of the derivative. All right, so we bring down the 2, so we have 2 pi times r, but the derivative of r squared is 2r times the derivative of what's inside. Okay, here again, we need the chain rule. So our time derivative of our area is equal to 2 pi r times the time derivative of r, or the rate at which it's changing. Well, we have that. The radius r is increasing at a rate of 3 centimeters per minute. dr dt is equal to 3 centimeters per minute. All right, so that means that dA dt is really equal to 3. This is 3. And so we have 6 pi r. Great. Part A. When r is equal to 6, find the rate of change of the area. This is the rate of change of the area. So we just substitute 6 in there, and so we get 6 times pi times 6 is 36 pi. Write that out here. 6 times pi times 6. In part B, it's saying, well, what is it when it's 24? Well, then dA dt is equal to 6 pi times 24. And now when we multiply that, it's 144. So that equals 144 pi. And that's how to solve that particular problem. Now, the idea here is the rate of change is the time derivative, which means that a is not necessarily a function just of r anymore. It's a function of t. So be very careful on those sorts of things. These are also called related rates problems. That one thing, the rate that one thing is changing affects the rate of how another one changes. Okay, a spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instant the radius is, and those are the two values, 30 centimeters and 60 centimeters. Something to think about. If I have a balloon here, and it's kind of small, and I pump a certain amount of volume into it, it's going to dramatically increase the size. If I start off with a great big balloon though, and I pump a huge volume into it, this has already got a lot of volume. If I pump the same amount of volume into it, I'm not going to get that big of a change. It might get a little bigger, but not much. And so keep that in mind. We really should see that the radius doesn't change as much with 60 centimeter at 60 centimeters as it does at 30, because the smaller balloon has less volume. So we're just going to kind of use that to check ourselves. How fast is the radius of the balloon increasing? And it is being inflated at a rate of 800 cubic centimeters per minute. Cubic centimeters, the cube refers to the volume. The volume of a sphere is given by 4/3 pi r cubed. So that being the case, let's go ahead and take the time derivative of both sides. And this is going to be, now this is 4/3 pi. The time derivative of this is 3r squared dr dt. The derivative of the outer function, 3r squared, times the derivative of the inner function. Okay? Chain rule. Loving the chain rule. So now as we kind of clean this up a little bit, you'll notice that the 3's cancel here, and we're just left with dv dt is equal to 4 pi r squared dr dt. Now, my question for you is, do you recognize this? Recognize it as, say, a different measurement of a sphere, like perhaps the surface area? Interesting that you take the derivative of the volume and you get the surface area. Huh. What if that happens all the time? Check it out, see if it does. But on this problem again, our rate that our volume is changing is 800, okay? So now we're going to use that. So dv dt is equal to 800. That means that 800 is equal to 4 pi r squared times dr dt. I'm looking for the rate that the radius is increasing. How fast is the radius of the balloon increasing? I'm looking for dr dt. So I'm going to go ahead and solve for that. Moving the 4 pi r squared over, I get 800 over 4 pi r squared is equal to dr dt. But I'm going to kind of clean that up a little bit and say this is 200 over pi r squared equals dr dt. All right, so now we can go back and we can actually plug some numbers in. So let's plug it in when r is 30. So we have part A. We're going to take 200 over pi times 30 squared equals dr dt. This gives us 200 over pi times 900 is equal to dr dt. And the hundreds cancel to leave me with 2 ninths over pi. And so this is going to be 2 over 9 pi is equal to dr dt. Now, going back, we said that if we blow the same amount of volume into a small balloon, part A, you'll get a lot bigger change. But if you blow the same amount of volume into a bigger balloon, you'll get a smaller amount of change. We should expect part B then to be smaller than part A. And so if we take this in, then we say it's 200 over pi, and this is 60 squared now, is equal to dr dt. This implies that this is 200 over pi times 3600 is equal to dr dt. And now the hundreds cancel again. The 2 becomes a 1, the 36 becomes an 18, and I'm left with 1 over 18 pi is equal to dr dt. It's not bad to use your intuition about a problem in order to guide yourself to the solution. It is perfectly legitimate. Draw a picture. It's okay. Reason it through a little bit. And then go back and see if your math matches up. Right now, we're looking at 2 ninths versus 1/18. That matches up. We knew that, hey, if you blow up a balloon and put the same amount of volume into it, since the balloon starts bigger, it's going to move less. Okay? That's what we found here in the math too. Don't be afraid to use your intuition.